Hello everyone. In this lecture, we will discuss motional electromotive force. So here we will use generator to exploit the motional EMF. So here the primitive model of generator is, suppose here we have a uniform magnetic field and this is a rectangular loop, and suppose this point is A, this is B, and this is X, and the width of this loop is H, and here this is a R. So R is nothing, this is a, suppose this is a light. So here in this case we have a rectangular loop and a uniform magnetic field. So when we pull out this rectangular loop with the velocity v, then the current flow in this loop, and the direction of the current is clockwise. So here the EMF is equal to magnetic force, and here this is a DI. So this magnetic force, this is exerted on a segment AB, and there is no any contribution of this horizontal part, that is BC and AD. So this factor is equals to VBH, and here V is the velocity of the rectangular loop, B is the magnetic field, and H is the width of the loop. Okay, so this is the EMF. This is equal, suppose this question is number 1. Next here we will find the relation between EMF and rate of change of flux. So here let phi be the flux and flux of magnetic field B through the rectangular loop, then phi is equals to B dot dA with integral. So here flux is equals to B dot dA integral. Then in our case, that is for rectangular loop, this phi is equals to BHX. So again, B is the magnetic field, H is the width of the loop, and X is the variable quantity here. So here as the we move the loop, then the flux decreases. So as the loop moves, the flux decreases. That is, d phi by dt is equals to bh dx by dt. So rate of change of flux is equals to bh dx by dt, or we can write bh, this is a velocity, here we have a negative sign. Suppose this is question number 2. So here when we compare with question first, this is EMF equals to VBH, and here d phi by dt is equals to minus bhy. So from these two questions we can write EMF equals to minus d phi by dt. So here the EMF, or more specifically motional EMF, is equals to rate of change of flux with respect to time. So this is the simplest case when we have a rectangular loop in a uniform magnetic field. Now here next we will discuss when we have a non-rectangular loop in a non-uniform magnetic field. So to understand this, suppose here this is a current carrying loop, and so here this is the point when the loop at time t, and this is the case for a loop at time t plus dt. So here this portion is the surface, and here this portion is the, we can say this is a ribbon like structure, that is here this is nothing, this is a ribbon. So suppose we consider this loop. Suppose this point is P and this point is a P dash. So a laboratory picture of this is that is here this portion part correspond to this, and this point correspond to this point. So here this is equals to di, that is this point is P and this point is P dash. So and this part is V dt. So V here is the velocity of the wire and dt is the time taken. And suppose the area of this rectangular loop is dA. Then mathematically we can write the change in flux d phi is equals to phi t plus dt minus phi t, and this is nothing, this is equals to phi ribbon, that is flux of ribbon, and this factor is equals to b dot dA of ribbon. Here, but this dA, that is infinitesimal area, this is equals to di. Suppose this is a length and this is a breadth, then we can write, this is a length, that is di, and this is a breadth, that is v dt. Then we can write v cross di with dt. Or from this question, this particular question, suppose this question is a number third question, then from this we can write rate of change of flux with respect to time. This is equals to b dot vi cross di, and here we have dt. Okay, so here we simply substitute the value of dA in this question. Suppose this question is third A. Here we simply substitute the value of dA. So rate of change of flux with respect to time is equals to b dot, here we put the value of dA, so this is v cross di, and dt will be di. Okay, so here v is the velocity of the wire. Okay, so if u is the velocity of the charge, then the resultant velocity W is equals to u plus v. So here we have W is the resultant velocity. Now we will substitute this velocity in place of v, we can write W. So here we can write d phi by dt is equals to b, this is a W cross d I, or we can write minus W cross B, and here this is a di. Actually this factor, that is W cross B, this is nothing, this is a magnetic force. Okay, this is the magnetic force per unit charge. So finally we can write d phi by dt is equal to minus f magnetic into di, and this factor is nothing, this is equals to EMF. Okay, or we can write EMF is equals to minus d phi by dt. So again, motional EMF is equal to rate of change of flux with respect to time. So according to this, either we have a rectangular loop in uniform magnetic field, or we have a non-rectangular loop in a non-uniform magnetic field. Then in always EMF is equals to minus rate of change of flux with respect to time. Okay, thank you.